Yeah.
Okay, I think this is a nice moment to give it a start. So I would like to welcome everybody here at the first Topology Optimization webinar. I would like to welcome you on behalf of the other organizers who are from DTU in Denmark, Ole Sigmund and Niels Orge, and from Delft, Yun Wu and Matthijs Langeraar and myself. Yeah, you probably have noticed that the number of participants exceeds our expectations. When we discussed, maybe everybody closes the mic.
Oh.
So when we started the idea, discussed the idea of having such a webinar, we thought, well, maybe the first session we have 100, maybe 200 participants. And this today it became clear that we have more than 400 people registered for this event. And unfortunately, our Zoom account can only handle 300. So some people will be disappointed. We will cover up for the next for the next meeting. And we will also post the recordings on the internet so that everybody can still see it. The nice thing is, from the registrations I saw this morning, was that we had already 100 registrations from Asia and more than 100 from US. So that means that the number of participants is very nicely distributed all over the globe. Yeah, so the initiative to set up such a topology optimization webinar was taken by Yun Wu. So all the credits go to Yun. Thank you, Yun. And his idea was, look, we have now this COVID-19 crisis. Conferences get cancelled or get rescheduled. It's very difficult to visit other groups. Traveling is very difficult. So it would be nice to still have a platform where we can keep the topology optimization community together, where we can exchange nice research ideas, get to know each other, and learn what we are doing. What we also hope as organizers, that this is an initiative which will last beyond the COVID-19 crisis, although nobody knows how long that will take at all. But we have already scheduled some upcoming sessions. You can find them on the internet. And the next session is scheduled for June 25, Central European Time, at 10 o'clock, and it will be hosted by Ole Sigmund and Niels Orge. With the top-up webinar, we try to target an international setting. And for that, it is important that participants and speakers come from all continents. And for that reason, as you look, if you look in the schedule, which is posted on the internet, you see that we have alternating times and days, so that there's always a shift when we move to the next session. And that, yeah, today, for instance, Sydney is very unlucky, but probably the next session, the West Coast of the US will be unlucky. But at least that we can always have participants of many continents. If you look at the speakers of today, also that shows a very nice international setting, 1 from Europe, 3 from Asia, and 3 from Americas. What we also like to mention, and we would also like to acknowledge their help, that's the endorsement by ISMO. And the ISMO also kindly helped us distributing last week the invitation. So for the first session, we have actively invited speakers based on recent publications published in different journals. And before we started this session, there was already a bit of chit-chatting about online teaching. And probably many of you have learned that online teaching has the tendency to be tedious, boring. So we thought that it was not a good idea to have very long presentations, but have short presentations. So for that reason, we have a keynote of the impressive 15 minutes, and then a normal presentation of only 8 minutes. And after every presentation, we would like to have a few clarifying questions and then a discussion at the end of the whole session, so after all the presentations, just to keep it quick and fast, that it is not getting boring. Also, I will just introduce the speakers very briefly. And of course, we are still looking for what's the best format for these top-up webinars. So if you have suggestions for improvement and feedback, please mail it to us. Don't use the chat because that information might get lost, but please send us an email if you have suggestions. Then I have a request. When we start the presentations, please all mute your mics. Do not try to share your screen. Of course, you can use the chat function to ask questions to the speakers. Be careful to whom you send something. If you don't like the chairman, please send it just as a private message. The speakers are requested, of course, to answer questions in the chat. For the speakers, I have the request to help me doing the time management, because my body language is not going to work. And once more, if you have questions, keep them to the end of the whole event, unless they are clarifying questions. And with this, I used my 5 minutes. So I would like to give now the floor to our keynote speaker. And the keynote speaker is Pierre Duysinx. He is from the University of Liege, Belgium. And I give the floor to you, Pierre. Please go ahead.
Thank you so much, Fred. So I will share my screen. Thanks a lot also for the organizers who fed our scientific life in this difficult moment. And I thank you very much for this. Can you see my screen? Yes, go. So let's go straight. I would like to thank also my co-authors, Eduardo, who is also the real hard worker of this team, and Maxime, a former PhD student who is now in Safran Aero Booster, who provided the nice industrial application. Since we are going to speak about the geometric constraints in additive manufacturing. So the motivation is to account for the additive manufacturing constraints. First of all, it would be size constraint, but also later on overhanging angles or avoiding closed cavities and ensuring sufficient interdistance between the bodies to evacuate the powders after fabrication. We also ambition to solve large-scale application. For an academic point of view, we will see the famous MBB beam revisited in 3D, and it has implemented thanks to a top-up code provided by Niels Oog from DTU and his co-authors. But the final application is an industrial one, which is designing a set of 3 brackets connecting an oil tank to the casing structure of a jet engine. This is a typical application from the company Safran, and they had plenty of design constraints like resistance, also fail-safe, and of course, being able to fabricate it using EBM, additive manufacturing process from titanium. And the basics of this is we start with the famous 3-field topology optimization scheme. Let's say that we have a density filtering scheme, followed up by the heaviside filter with a couple of parameters. We have the density filter, the size of the density filter that we will talk about later on. We have the beta and the mu, the thresholding parameters. And finally, we adopted also the robust design approach that was recommended by Ole. And so we will have this dilation, intermediate, and eroded structure we talked about. So these 3 structures, eroded, intermediate, and dilated, will be accounted for. And one major question was to ensure minimum solid and void sizes in these constraints to have a feasibility, to have an indirect feasibility of the blueprint design, which is the intermediate one. So this means that a lot of questions from the industrial people is to how to select this design, the ball of the filtering and the thresholding of the heavy side, the smooth heavy side function. And so one question was to find analytical and numerical relationships which can help the designer to select automatically the numerical parameters from the final minimum size of the solid void, and also later on the thickness of eroded and dilation after when we will talk about the maximum size. So this has been provided and has been published today on a paper by Eduardo Fernandez. I will provide you the hyperlink at the end. The second ingredient is maximum size constraints. Maximum size is limitation of the number of voids or increasing the number of voids in a given reference balls. To facilitate the handling of the constraints, the many local constraints, Eduardo and his co-authors has also provided a nice technique, some aggregating all the constraints using p-mean and providing a relaxed formulation that is denoted by GMS, so maximum size of the domain. A very interesting fact is the finding that it's better to use the annular size of the reference domain to calculate the maximum size, since the inner ball is already dominated by the minimum size. And so this is a very nice improvement, as you can see here, because the annular region helps to circumvent the famous drawbacks of circular regions and many inclement hotspots on many drill holes into the final optimized structure. So the question is now, we have to adapt also the different size of the minimum size and maximum size reference balls to the fact that we play with the eroded, intermediate, and dilated structure. And this is a part of the work that to calculate the different and automatically to calculate the different size for the three structures that will be calculated during the calculation. And you see here that on the bottom side, the right-hand side, the different size of the balls that will be adapted for the eroded, intermediate, and dilated sides. And the effect is shown here in solving the MBB beam. You see only 1/4 of the structure because we use the symmetry planes to help handling the large-scale problems. And we have 3 constraints, one for each of the robust design subjects. And you can see clearly the size of the maximum size, breaking bulky parts in the design and ending up with small plates instead of having big, thick bars. So it's also a nice, interesting result because in that case, we converge to plate structure instead of having some beam structures. The third ingredient is maximum size is also a nice way of introducing minimum gaps, separation of between solids parts, and having the same constraints, but with different reference size. You can see that the GMG, the big ball, is for separating the parts, and while the smaller balls is to ensure the maximum size. So minimum gap and maximum maximum size are brothers, but different size. That's why in the following, you will have the two sets of three constraints, one for the maximum size, the omega test domains, and the psi, which is the bigger ball, about the minimum gap constraints. Now, let's go for the application, and you see here the effect of the robust approach and the max size and the minimum gap, which helps to separate the different geometrical entities, the structural members, finally increasing the minimum size and minimum gap in between the different ones, helps to separate clearly the structural walls of this MBB beam. It looks like finally like a roof structure where the people have to assemble timbers, making frames with a kind of separation, which is a kind of inspiration that we could interpret from the optimized design that we got from this classical academic benchmark. So we can enjoy a little bit the visualization of that if you have it. And that helps to understand that big thick walls will be separated into several walls well separated for evacuation of the powder. Finally, just a few words, the treatment of boundary condition is also necessary. And so you could refer to the paper to see how the tricky sets of application of the boundary condition to avoid the drawbacks, artifacts related to that. Let's come to the industrial application. That now we start from our industrial problem where people wanted to minimize the mass. Of course, we can imagine that we can have some compliance minimization and how to treat the strengths, the material connectivity, which is an implicit damage resistance, and also the manufacturing constraints. We reworked a little bit the formulation with the company, finally minimizing the compliance with some sets of volumes. Trust constraints was unfortunately available when we did the application. It was treated as a post treatment, and we had also the 3 sets of minimized size, maximum size, and minimum gap that were involved. Just a few words also, the application of the load case were using some pseudo acceleration force, a D'Alembert acceleration force, along the main unidirectional, the main principal axis of the body. And we had the loads to be taken by each of the 3 brackets that was possible. Later on, it will be possible also to use flexibility of the oil tanks using super elements as well. So I'm just skipping a little bit the construction of the topology domain, but we had also to prescribe some non-design domains along the fixations and the application of points of the loads coming from the inertia of the oil tank. Just a word about the application. We had a problem about CPU time to take into account the fact that we have a series of damage possible in the fixation. Finally, it was a solution that was too expensive to have these kinds of possible damage scenarios. And we adopted a much more cheap solution that was to account for a weighted sum of the compliances, which gave us in that precise example, particular example, the same topic. Finally, we had the final process, the final polishing of the structure. Optimized structure was reconstructed. We introduced that body into a CAD software that was Annex, in Siemens Annex in that case, using the smoothing and reverse engineering processes to finally go for the post-processing of the stresses, verification, and virtual processing, virtual manufacturing and rendering of the structure. So the stresses were evaluated. We had different scenarios about mass saving in the evaluation, and we find that the good level of stress level compromise between mass saving and stress increasing in the bodies were to use this volume of 5.6% of the design constraints, which ended up with a 94% reduction of the mass compared to the bulky design. And you can see here in blue the different targets. We have different mass scenarios. The blue one, the bracket 1, the bracket 2, and the bracket 3, which look very elegant with their organic shapes, are the ones that were selected finally by Safran to be designed by manufacturers. Just a few words about the fact that we assumed that we had a load case without no redistribution of effort. Finally, we made the final verification, and we can see that the mass, the reaction, the force redistribution is not so important, so we can keep the final solution as it is. So just, we don't have to waste our pleasure. Look at the beautiful organic shapes of the brackets. when you introduce from left to right the maximum size and the minimum, the maximum size and the minimum gaps, which ends up with very well, very elegant shapes and very funny from a structural point of view. So this is the virtual prototyping with the different ones. Maximum gap is maximum size in the middle, and minimum gap is on the right hand side. So this is the 3 brackets finally produced by the company as a virtual shapes. So thank you very much. This was a proof that we had this robust formulation is very successful, complemented by some minimum size, maximum size, and minimum gaps. And we can show that it is also now able to solve large-scale 3D problems in a real load case and design environment from companies, which is also the great objective of our research, is to transfer to the site. The code is available in GitHub, and so you can download it if you want to play a little bit with the code. And finally, let's say that the story is still going on with some work now on wire-based additive manufacturing and other kinds of additive manufacturing, but also introducing the stress constraint as soon as the preliminary design. And I would like to thank the co-author for also the sponsors who made it possible to have this nice research with the help of the companies that were also very collaborative. And so you can download the papers, the one from SMO, but also the new one that has just appeared in MAME. And I will send the hyperlink to Yungu so that you can download it immediately after the conference. Thank you very much, Fred. Thank you very much, Yungu. Thank you very much, Ole. And I'm ready for any comments, clarification if necessary.
Thank you so much, Pierre. And also thank you for being so well in time. So there's time for a few clarifying questions. Who may I ask to invite to have a question for Pierre? Anybody? Please open up your mic and feel free to bring forward a question for Pierre.
I could have a short question, Pierre. Thanks for a nice presentation. I was just wondering, you started with this analytical derivation of the length scale imposed by imposing the robust filter. We had some predictions on that in the original paper. I'm just wondering if you had, were the new predictions different, or did they cover more than that?
Yes, it was extended since you had the different parameters centered at about 0.5. So we have now predicted the things in all the different cases, so that it's available for the user. He wants to change that, he can automatically predict the nice numerical parameter from the final practical diameters and so on he would like to guess and the final optimized design. So it's extending, and it's also, we have an analytical formula which it's more interesting to have a fast response.
Okay, interesting. Thank you.
Thank you so much.
Any other questions from the audience? Then I have one. Pierre, if you have this gap constraint.
Yes.
Could you imagine that you make it slightly more sophisticated, that you only have a gap where you need it because you want to avoid contact?
Absolutely, yes, because now we cover the full design space, but we could have a well-targeted part. So we could have that, yes.
But that part might be design dependent, eh?
Yeah, so you can have a smart strategy by adaptive one. Probably you would have to start from a rough design and then insert progressively the constraints along with the design bursts and the effect where you determine. If you can also use a segmentation, determine the boundaries, and you can maybe have a prediction of the place of interest.
Okay, yeah, that would be interesting. Thank you very much. Okay, thank you once more, Pierre, on behalf of all the participants.
Yeah. Then
thank you so much.
Looking forward to seeing you. To
Okay.
share coffee with you.
So we go further. And the next presentation will be on multi-material topology optimization of lattice structures. It will be presented by Julián Norato from the University of Connecticut, the US. Julián, the floor is yours.
Thank you, Fred. Can you hear me?
Thanks. Oh, yeah. I'm going to mute.
Excellent. All right. So I'd like to start by thanking the organizers of this event for inviting us to share our work and for putting together this webinar. Today, I'd like to talk about our work on multi-material topology optimization of lattice structures using the geometry projection method. The first thing I should say is that this work was performed by my PhD student, Hesaneh Kazemi. So everything that you're going to see here is her work. She just defended recently and is going to be taking a postdoctoral position this summer. And I also would like to thank the National Science Foundation for funding this effort. So we're interested in truss lattices. Truss lattices are architected materials that are cellular solids. That means they are porous. And they have several features that make them attractive. One of them is that they have an open cell design, and that makes manufacturability with additive manufacturing techniques a little easier because you can remove sacrificial support material. Also, the porosity can actually have a function, as in the case of porous bond scaffolds, where you may want the bond to grow inside the lattice. And they provide a high degree of redundancy. Now, we want to look at multi-material lattices because if you now have multiple materials available and those materials have different modulus to density ratios, then there is an opportunity to get a better stiffness for the same weight than a lattice with a single material of the same weight, or conversely, you can get a lighter lattice for the same stiffness. Also, if you manufacture the lattice so that you have one strut made only of one material, then that makes it a little easier to manufacture than if you distribute the different materials arbitrarily within the design region. And finally, you may have the potential for multifunctionality if the different materials have different functionalities in different physical domains, but that is an aspect that we didn't explore in this work. This is a graphical summary of our method. We start with this initial design, which corresponds to the periodic unit cell of the lattice. The spheres that you see here are near zero length bars, and each bar is made of a mixture of available materials. So the designer specifies a set of available materials, in this example 3, with say different moduli and different physical densities. And we employ a continuum mesh for the analysis, and we also impose some desired material symmetry. So for instance, we may want the lattice to have cubic symmetry, orthotropic symmetry, etc. And what our method does, what we wanted to do, is that it finds the optimal layout in space of these struts, including potentially removing some of these struts, and at the same time, it determines the best choice of material for each one of the struts. The existing approaches to lattice design are primarily the ground structure, a topology optimization method, and the density-based topology optimization method. Ground structure is, as the name indicates, it's a ground structure of 1D elements. And so the modeling accuracy is not as good as a density-based topology optimization, but on the other hand, the computational cost is much lower. Ground structure methods have obviously less design freedom than density-based approaches, but we could argue that because they render open cell designs, that they are easier to manufacture than the closed cell designs that you may obtain sometimes with density-based topology optimization. Our approach to tackle this problem is to employ the geometry projection method, where we essentially describe the design, the lattice in this case, as being made by the union of some geometric primitives, for example, bars. And the idea of the geometry projection method, which we developed first for shape optimization in 2004 and more recently for topology optimization in 2012 and 2015, is that you take these high-level geometric parameters, say the endpoints of the axis of this bar and the width of the bar, and you smoothly map them onto a continuous density field on the design region. And as we do in density-based optimization, for instance, then we take that density field and we define an ersatz material for the analysis. In the particular case of multi-material lattices, we have to account for the fact that we have multiple materials, and so we define an effective density per material per bar, and then we add constraints to the optimization that make sure that at most one of the size variables corresponding to each material to each bar is 1, meaning that one strut can be made of just one material in the optimal design, and that all the size variables for the materials are either 1 or 0. I won't go into the details for the sake of brevity, but I'm happy to answer any questions about this formulation afterwards. So if we compare the geometry projection approach to the other two approaches, to ground structure approaches and density-based approaches, we inherit the modeling accuracy and computational cost of density-based methods for better and worse. But we have a design freedom that is somewhere in between ground structure approaches and density-based approaches. We obviously don't have as much design freedom as density-based approaches because the lattice has to be made of these cylindrical struts, but we have more design freedom than ground structure approaches because the connectivity is not fixed. These bars can sort of move freely inside the unit cell. And because we end up getting open cell structures, then they are easier to manufacture. We also impose in our method symmetry and what we call no-cut constraints. The symmetries are so that we obtain desired material symmetries for the effective properties of the lattice. So in this particular example, say we want to have cubic symmetry. And so you have 9 planes of symmetry, which give you this reference region, which is a tetrahedron. And the way we accommodate symmetry is fairly simple, which is that we just reflect the points at which we compute the projected density with respect to the symmetry planes. And we can do that for an arbitrary number of symmetry planes. And then we just compute the projected density. And so essentially, we only have bars defining this reference region. And the no-cut constraint ensures that no strut is cut either by the symmetry planes or by the boundaries of the unit cell, because otherwise we end up with these partially cut struts that give us designs that are a little more difficult to manufacture. So I'm going to give 2 examples of problems that we solved with this formulation. One is to maximize the effective bulk modulus of the lattice. The other one is to minimize the Poisson's ratio. We're going to employ these 3 materials, which are made up materials with different moduli and physical densities, and we enforce cubic symmetry. One interesting feature about our formulation is that we impose a weight constraint, and we like that because with a weight fraction constraint, the optimizer chooses the right proportion of the different materials as opposed to imposing arbitrary volume fraction constraints on each one of the materials. These are some of the results for a bulk modulus maximization using 2 materials. And so these are the kinds of designs that we see. The top row gives us the isometric view of these designs, the bottom row, the side view. And some of the layouts are, resemble familiar designs like the Otter truss, but some other ones are not necessarily so intuitive. And perhaps more importantly, the choice of material for the different struts is not intuitive. These 2 material designs satisfy physical bounds, so that is good. We're not violating any physical law. But as a matter of fact, they're also not close to the bounds, and we expect that because these are open cell designs. We know that the stiffest lattices are closed cell designs. These are examples for bulk modulus maximization of 3 materials. So one of the advantages of our formulation is that we can readily extend it to any number of materials. And so now, the layouts, again, are not so intuitive, and the choice of material for each one of the struts is also not intuitive. And here we have just a little movie showing kind of a rotation of one of these unit cells so that we can visualize it. We also have an example of Poisson's ratio minimization for 2 and 3 materials. These are the kinds of designs that we get. The 3 material design is the one on the right. In this particular case, it was just more difficult to find a weight fraction constraint that would have 3 materials. But we know that for the same weight fraction, we get a lower Poisson's ratio if we use 3 materials than if we use 2. And these look like the usual reentrant honeycombs. So that's good. And this is just a little movie with the showing one of these designs. Okay. So to try to stay on time, let me wrap up with some comments. The first one of them is that we actually wanted to fabricate some of these lattices and test them, mechanically test them. But what you find is that the polymeric materials that are used for some of these multi-material printers have similar physical densities. And that means the optimizer just uses the stiffer material, particularly when we're trying to maximize bulk modulus. One thing that we're that we're examining right now, that we're studying, is to impose minimum angle constraints, which we already have done for structures, to prevent overlaps among struts that make manufacturing more difficult. And the other possibility that we're working on right now is to have struts that are either hollow or fiber reinforced. So with that, I went a little bit over, but thank you very much for your time. And I don't know if we'll take questions now or at the end of the short talks.
Thank you very much. Thank you very much. Let's check if there is an urgent clarifying question. If not, then I suggest to thank you, that we thank you again, and that we move on to the next speaker. And the next speaker is addressing stress constraints in compliant mechanisms using a level set topology optimization. And our speaker is Emílio Silva from the University of Sao Paulo in Brazil. Emílio, the floor is yours.
Okay, thank you, Fred. Can you see my screen? Everything
is
okay?
Yeah.
Okay.
You can see it. Perfect.
So, thank you, Fred. So good afternoon or good evening. So good morning, good afternoon. So I'm Professor Emílio Silva from the University of Sao Paulo, Brazil. At first, I'd like to thank the organizers for inviting me to give this talk, and also congratulate them for the organization of this successful event. The title of my work today is Stress Constraining the Level Set Topology Optimization for Compliant Mechanisms. This work was developed together with my fellow Dr. Hélio Emmendoerfer and the Professor Eduardo Fancello. I'd like to give special acknowledgements to the Brazilian sponsors that support this research. So that's the outline of my presentation. At first, I give a brief introduction about compliant mechanisms and the objective motivation of applied topology optimization to design compliant mechanisms considering stress constraints using the level set approach. I present the stress constraint in the primary formulation, the level set update procedure using via reaction diffusion equation, sensitivity analysis. I present some numerical results, and finally the final remarks. Well, compliant mechanisms are mechanisms where movement is given by the flexibility of a structure instead of the presence of joints and beams. A classical technical difficult when designing compliant mechanisms is the emergence of non-realistic flexible joints or hinges. Essentially, the stresses that exceed the material the failure limit. A natural way to overcome the occurrence of hinges is the inclusion of stress constraints within the topology optimization problem. So the objective of this work is to apply topology optimization to design compliant mechanisms subject to local stress constraints using the level set approach. We aim to create an algorithm able of identifying stress concentration regions that arise as hinges. As a main contribution, we are using augmented Lagrange approach and level set implicit boundaries to handle local stress constraints. And the motivation, we want to come up with hinge-free designs by controlling the stress level, and it's a topic still open to research. So regarding the level set based formulation in the structural domain, the regions are implicitly defined by the level set function phi. So when phi is positive, you have the strong material or the solid material. When phi is negative, you have the weak material or the void material. When phi equal to 0, you have the boundaries. And here we have distributed springs in the output port in the direction of the desired displacements. The optimization problem is posed as maximize the output displacement and minimize the displacements in the input port. We have to satisfy the equilibrium equation, and we have defined local stress constraints. Our constitutive tensor is given as a function of the constitutive tensors of the strong and the weak material. H is the Heaviside function, and P is an exponent which allows us to differentiate the constitutive tensor in relation to the level set function phi. So the goal is to define a stress constraint function that follows a continuous variation during the movement of the boundary. So we define a finite number of stress constraints in the so-called sample points. We also define a neighborhood around the sample point, and also an area fraction of solid material in this neighborhood, which is given by this integral. In this work, the sample points are the nodes of the finite element mesh, and the neighborhood is a square area of the same size of the finite element size. And so we define stress constraints along the entire domain, and the number of stress constraints are equal to the number of nodes of the mesh. Regarding the stress constraint, we are defining it in terms of the von Mises stress, and we multiply it by this psi function, which is given in terms of the area fraction solid function. So this psi function essentially enhance the stress values of the sample points that are cut on the boundaries. So essentially, you have this exponent key here. So if key, for example, is equal to 0, this psi function will enhance the stress at sample points next to the boundary, even if the area fraction has a small amount of solid associated to the neighborhood. However, if you consider very small values of Q, we may get some high oscillations in the stress constraint. So in this work, we adopt Q equal to half. We are solving the optimization problem by using the augmented Lagrangian technique. So essentially, we add the stress constraints to the objective function by defining this linear term with Lagrangian multipliers and this quadratic penalization term. So it's a very efficient method to deal with large number of constraints. Regarding the level set evolution technique, we have defined this regularized objective function, or essentially we add this regularization term to the original objective function, and the evolution of the level set is given by the derivative of this regularized objective function, so resulting in this reaction diffusion equation. So this method requires no reinitialization of the level set function and allows for the creation of new holes. And this term here is the so-called reaction term, which is obtained by using sensitivity analysis. In the sensitivity analysis, we use the Lagrangian method. We obtain the total variation of the Lagrange, and then we obtain the state and joint equation, we solve them, and then we can obtain the derivative of the objective function in relation to the level set function, which is essentially the velocity field, the natural extender over the domain. Now I'll present some numerical examples. In all of them, we are using the material properties of nylon. We are using the real properties. And here we have the corresponding optimization parameters. So the first example is the traditional inverter mechanism. So the objective here is to obtain a hinge-free design. So that's the initial domain with the input port, the output port, some boundary condition. So here we have the initial level set configuration. So we have solved the problem considering stress constraint and without stress constraint. So when you consider the stress constraint, we come up with a hinge-free design where the stress constraint is satisfied. When we do not consider the stress constraint, we come up with hinges and stress concentrations. So it shows that the objective function proposed does not prevent the appearance of hinges. Hinges are avoided due to the stress constraint. We solve the same problem by changing the volume weight factor. That's the factor that multiplies the volume fraction term in the objective function. As expected, as we increase the value of the weight factor, we decrease the volume of the structure domain. In all cases, we obtain a hinge-free design and the stress constraints are satisfied. We also validate our stress constraint design problem by post-processing in a commercial software. So you can see here that the post-processed result is still satisfy the stress constraint. And when comparing the displacements of the topology optimization result and the post-processed result, the difference is less than 1%. Next example, we consider this L-shaped mechanism. Essentially, we have introduced this geometric singularity here, where there is a natural stress concentration. So here's the input port and here's the output port. So we have solved this problem initially with initial configuration with no holes, and we come up with this topology here, which shows that the method can create new holes. And then we solve it again with this initial configuration with holes. We come up with this topology here, which is different. However, both of them, they have approximately the same volume ratio. Both of them are hinge-free designs and they satisfy the stress constraint. And this example shows the influence of the final design for different initial configurations. We have solved the same problem without the stress constraint. So we come up with hinges and the stress concentration here. So here you can see the displacement, the deformity shape topologies of all these results. In all of them, the functionality is attained. So here I have a video of the level set procedure where you can see how the optimization moves. As a final remarks, optimized design is converged to hinge-free compliant mechanisms. Stress visibility is achieved locally everywhere in the domain. Numerical examples are considered real properties, material properties, and the local nature of stress constraints reinforces the existence of local minima and consequent dependence on the initial gas design. As a future work, we want to extend the present formulation to multi-material framework. So that concludes my presentation. Thank you for your attention, and I'll be happy to answer questions.
Emílio, thank you very much. Also, thanks for being very nicely in time. Is there any clarifying question? If not, then I have a short question, Emílio. You use the stress constraints at the sample points. Would it be possible to recover the stresses at the boundary of your interval, of your domain, so that you bring it to the level set, the interface which is described by the level set?
Yeah, I believe it's possible. We have considered only the stress in the sample points, but I think that using the level set, and we can recover in the boundaries. Yeah.
Okay, thank you. Any other clarifying questions? Well, Emílio, thank you once more. And then we move to the next presentation. The next presentation is addressing transient sensitivity analysis of particle motion in steady state laminar flow. And it will be presented by Keulen from Hanyang University in Korea.
Yeah. Hi,
floor is yours. Yes, we can hear you and we see your screen.
Yeah, thank you very much for the nice presentation. And in this presentation, I would like to share my research for the particle motion control using the topology optimization. So first of all, I want to introduce the research objective and why we needed to consider motion of the particle, and then topology optimization formulation considering the particle, and also some sensitivity analysis. And also some numerical example showing the potential and validating the proposed approach, and also the conclusion. So it is very important to control the motion of the particle, microfluid. For example, see this figure, sorry. So there are some green dot and a small red dot. And if we give some flow from the left to the right, and due to the difference of the inertial force, so the particles are separated into the different channels. So one of the main the way to control the trajectory of the particle is to design this flow channel to utilize the viscosity force. And also, there are several approaches to apply the external load to control the motion of the particle directly. So this is a very important subject, and nowadays it becomes more important due to the crisis and outbreak of the COVID virus. So I found that in topology optimization, we can design some layout of these micro channels. So I tried to challenge this subject. So we needed to analyze this coupling system first for the optimization, and then we needed to change the trajectory. So in order to solve this coupling system, I solved the Navier equation. So see that we have the equation for the steady state laminar flow, and here we assign the viscous force. So this is added to design the pseudo-rigid body. It means that we can assign very large viscous force to model the pseudo-rigid body. And after getting this U, then we can plug this to this Newton's second law. And this equation is the Newton's second law. But as you know, if we have some finite particle, we needed to consider rotation of the particle, but we neglect that. So not only the one particle, but also we needed to the multiple particles. And in this simulation, to solve this Newton's equation, we have the use the numerical scheme. So steady state equation and the transient equation. And moreover, when we have some constraint among the particles, we need to add the geometric constraint. And in this simulation, I employed the shake algorithm. So for the analysis, for the optimization, we needed to derive the sensitivity analysis. And here we adopted the objective function with the velocity. So we have the Newton's equation and the steady state laminar flow equations. Then in order to obtain the sensitivity, first of all, I solved this adjoint system for the lambda. Then this lambda is plugged into this second adjoint system, so psi. Then we insert this one to this system of equation. And one of the main challenges of this equation is that even though the fluid is steady state laminar flow, this is included in the integration of the time domain because we needed to derive this equation. And the first adjoint system can be solved with the time reversal integration. And because the lambda can be interpreted as a velocity, in a time reversal integration, we should put the minus for the lambda. And we have the publication here in this year. And I found that Anderson also published the similar research. And in addition to that, I wanted to impose some geometric constraint among the particles. For example, if we have no constraint among the particle, then particle can flow without any restriction. However, with the geometric constraint, it means that we want to impose some distance or the angle or boundary distance. Then we needed to analyze the system of equation with the geometric constraint. In order to impose that constraint, I added this FC, which is known as a constraint force. And basically this idea is that we applied some contraction force when the particle closes. Then we apply the reverse force when the particle become longer. So because this is actually the stiffness matrices, so we added this matrix to the adjoint system application. So this is the numerical example. So this is a fluid input, and initially we distributed the 4 particles, and I wanted to gather this particle in some areas. For the optimization, I used the variation of the position, and I also added the variation in the y distance. So this is the result with the 4 particles, and we have some channels, and we have some curved structure to control the trajectory of the first particle rendered by the green dot. So interestingly, this blue dot travels shorter, and this green particle move the longer trajectory to meet at this location. And I do some elaboration to analyze the 100 particle. You may think that it's very easy, but we found that it takes a lot of time to improve the topology optimization code to consider this many particles, and we have this nice structure. And this example showed some example with the shake algorithm. It means that with this 6 particle, we imposed some geometric constraint. So initially, they are aligned vertically, but when we have some flow, then it rotates and meets at here with the same optimization formulation. So this is the conclusion. We designed some fluid channel to collect the particle, and in order to solve this problem, we needed to develop some adjoint system of equation. And in this research, I found that topology optimization can be defined as a life-saving tools. For example, if we have the spread coronavirus, then with this wonderful theory, we can design the particle and we can design the topologically optimize the white blood cell to eat the virus. So yeah, this is all I prepared today. Thank you very much.
Thank you so much, Gilho. Thanks very much also for keeping in time. Are there any clarifying questions at this moment from the audience? If not, thanks once more, Gilho. And
thank you very much, Alberto.
We continue to the next speaker, and the next speaker addresses deep learning-based methods for the microstructural materials design, and it will be presented by Wenjing Yi from Hong Kong University of Science and Technology. Please, the floor is yours. We do not hear you yet.
Okay, I have not speak yet.
Ah, okay.
All right. Oh. Sorry, I was playing with license. All right. So first of all, thank you very much for the invitation, and it was my pleasure to present our recent work on deep learning method for the design of microstructure in this webinar, okay, which I think is a great event. All right, so since we have a very tight limitation time schedule, so I'll just go directly to those issues, the two issues I'm going to talk about today regarding in the conventional topological organization methods. The first one is load efficiency. Almost all the TO methods require repetitive evaluation of object functions, constraints, and sometimes sensitivity analysis as well, right? So these are often conducted using high-dimensional simulations, which is time-consuming. So for problems with large size, particularly the 3D problems, the design process can be extremely slow, as in some sense, it will actually severely limit the application scope of TTO methods. Oh, there's also another situation that though in those applications that require a large set of design. For example, in the design of functionally graded materials or heterogeneous materials, right? So they need a lot of unit cell designs with different properties. Even though each unit cell may not take that long, but the accumulated time for so many of the design could be quite significant. So the second issue is regarding the difficulty in imposing shape control, shape constraints, mainly due to the lack of explicit representation of the design. Though shape control obviously is important, as actually previous few speakers already also talk about how to constrain geometric constraint, how to constrain the shapes to reduce the stress concentration, right? So what I show on this figure, in fact, is a hypoelastic material, elastomer material used to control the elastic waves. This was designed using the simple method. As you can see, the shape is quite, well, it's pretty, but it's going to be very difficult to manufacture. And moreover, it has quite a lot of those sharp corners in which they were definitely going to have a stress concentration. Right? So shape control is definitely important in those kind of designs. So there are a lot of methods out there to dealing with my two issues, right? So today I will focus only talk about those methods based on deep learning. So roughly, there are two groups of methods. The first group is to using different ways to try to accelerate the TO designs. So there's a method which developed with using a neural network to map the intermediate designs directly to final design. So to shorten the design cycle. And another type is directly just using network to output the optimal design directly from the prescribed boundary condition and the loading conditions. The problem with those two problems, or the issue with those two type of approaches, it needs to generate a very large set of training data. And these training data are a bunch of optimal design, and they have to obtain from the conventional TO methods. So those type of methods are only suitable for those design in which you need to have a lot of design for the same setting of the problem. So there's another type is to using neural networks serve as efficient surrogate models to perform the forward calculation and all sensitivity analysis, and to incorporate those surrogate model into the TO algorithms. Okay, so we call these accelerated TO algorithms. Now, if you do it, if you're using the right generative methods, you could end up a much smaller set of training data compared to the previous method. So here I'm just gonna show one example, which the recent result we have to design the material with a Poisson ratio, negative Poisson ratio, and with a prescribed volume fraction in range prescribed by here. So what you see here as a bunch of designs correspond to different volume fraction and with different target Poisson ratio. And the network, the accelerated simple method algorithm, this is the results given by the accelerated simple algorithm, sorry. And if you look at the design error, compare the target value, all of these designs actually is less than 6%. And this is achieved by using only 2,000 training data to achieve that. And in terms of efficiency, using neural network to perform forward calculation, it is about 137 times faster than FEM calculation. And for sensitivity analysis, that's about 74 times faster. So these indicate neural network, once it's constructed, it could be extremely faster than the FEM calculation. Well, previous type of approach are all actually connected with TO method itself, right? The next one is we're going to talk about is the design network, which is purely network based and is totally independent of the TO methods. A key components in this type of method is these generative models. Okay, for example, we have generative adversary network again, or the variational auto decoder VAE. So these generative models, the nice thing about these generative models, so once it's trained well, it actually provide a low-dimensional vectors, or you can call descriptors, which can successfully characterize the structures with certain features. So we can use this generator to generate design candidates. So these design candidates will have certain features we want. So to implement that, all you need to do is just generate a bunch of training data has that kind of feature. So once it's trained, the generator will automatically generate new images or new structures within the same features. So once we have the generator generate design candidate for us, so in a way it defines your design space for you with a certain shape constraint there. So once we have the generator, it can connect to a convolution neural network. The function of the CNN is to map the structure with its structure properties or material properties. So it's a perform regression. So we have this connected network which map a low-dimensional vector that basically generate a structure for you to the structure response directly. And the entire network is analytical. So we can use in backpropagation to find the suitable impact in suitable vector, which leads to a structure that satisfies the design output. So that's how we perform the inverse design using that network. So to see the performance of the GAN, so here's a couple images, several images we have. So this is the initial image, meaning the training data we provide to the GAN to train the GAN. And these are the images generated from the GAN. And so you can see the features we have is, first of all these holes, the white part denote holes or inclusion. They are more or less elliptical shape, and then the black part denote the base material. So there are two features. One is all these holes inclusion are ellipses, and then the black part should be connected. As you can see from generated image, these two features captured very well. Well, if we look at a little bit more complicated shape, if we mix the square with circles, and the GAN can also provide satisfactory images with the same shape and constraints. So moreover, the volume fraction, the distribution of the volume fraction can also be preserved. So is the distribution of the number of ellipses. So this shows the distribution of the number of holes in the original data and in the generated image. And you can see these two agree well. Sometimes in some applications, you won't actually control the number of these inclusion or hole exactly. So using some conditional gain will be recently we're able to get to control the number very precisely. So here it shows a bunch of square dots, right? The number of squares in each of these figures is exactly 20. So these square dots actually represent some heater. So the problem is to perform thermal management. We want to design the layout of heaters so that the maximum temperature is the minimal. All right, to see some design results, I'm going to using the example presented in the paper published in SAMO recently. So this is to design a microstructure material with a porous structure. It's a porous microstructure material. And we want to design structure with a certain complex tensors.
Can you try to finish up in roughly speaking 1 minute?
Sure, almost done. So here are a few examples, few design solutions with circles and square. And here's the results of these corresponding the complex tensors. And I will just directly show you these tables, which give you the relative, average relative errors of these of the design value compared with the target value. So all of these is less than 5%. So to conclude, basically there's a certain features about the design network based on generative models. First of all, to generate data, you only need to forward calculation. So this method can be applicable to those problems which you don't have sensitive information or difficult to get sensitive information. The second is very efficient. For this particular design problem, the CNN calculation for the predicted complex tensor is 0.034 seconds, and the FEM takes 0.8 seconds. So this is roughly about 3 orders magnitude improvement. And the entire design is around 1 to 5 seconds per structure. So it's very general, suitable for a wide range of problems. So in regard of what kind of physical problem you have, and it can handle geometry constraint, some geometry shape relatively easily. So that pretty much concludes my talk, and then we're happy to answer to any questions you have.
Thank you very much. So from the audience, is there a quick clarifying question at this moment?
Yes, I have a question. To understand the results of your design problem, is this to imply that you would like to directly manufacture the microstructure that you find, or what am I supposed to be building based off of this?
Oh, I mean, for that particular design problem, you're building up, you manufacture a porous microstructures. So
with exactly the microstructure that you're showing.
Yeah, so these can be microstructures in for example, functional grade material. This is just one microstructure design. So you can design many of them and put them together to realize certain functions. I don't know if I answered your question. So in terms of manufacturing, you can directly manufacture that porous material using, for example, additive manufacturing.
You did. The follow-on question then is that if you have complete control over what you're manufacturing, what's the benefit in having the GAN generate specific microstructures? Why wouldn't you just open up the design space to any microstructure, since you're going to be building it anyways?
For example, there are certain, for the composite material, particle reinforced composite material or fiber reinforced composite material, which this inclusion has certain shape. So you have to make sure that your structure contains certain shapes.
Okay, so with respect to time, I think we stop here the discussion or the clarifying questions. Thank you once more. Thank you very much. And we move on to the next speaker. And the next presentation is on multi-material thermo-mechanical topology optimization in the context of additive manufacturing. And it will be presented by Olivier Giraldo Lodono, and he is from Georgia Institute of Technology from the US. Floor is all yours.
Thank you so much. First, I want to thank the organizers for putting this webinar together and for extending the invitation to us to present this work. So, as you already indicated, my name is Oliver Geraldo Londono. I am a PhD student at the Georgia Institute of Technology, working under the guidance of Professor Glaucio Paulino. And today I want to present to you a paper we recently published on multi-material thermomechanical topology optimization with applications to additive manufacturing. We use this formulation to design multi-material parts as well as the support structure to be used in additive manufacturing. The work is based on this paper, which you can download from CMAME, and this paper was published in May. So to motivate this work, topology optimization involving thermal fields has been used, for example, for the design of heat sinks or heat exchangers. But recently, there is a trend to use topology optimization involving thermal fields to design the support structures for additive manufacturing. And only a handful of studies have considered the thermal effects in the designs. And here I share 3 of those examples for you to see. As you can see in these designs, many of the topologies have regions that are connected to the main part, which are too thick and can be very difficult to remove after the part is being printed. Our designs, as you will see later, lead to a branch-like connections to the composite part, such that the removal of the part after the print is finished is easy. To solve the topology optimization problem, both for the design of the composite structure as well as for the design of the support structure, we use this topology optimization statement. Here, the design variable vectors, we consider M design variable vectors 1 per candidate material, because we are dealing with a multi-material topology optimization framework. So we have M candidate materials, and we define an objective function, which is a convex combination of a mechanical objective function and a thermal objective function. For the mechanical objective function, we consider the traditional compliance, and for the thermal objective function, we consider thermal compliance. We use these 2 objective functions with the aim to obtain support structures that are both stiff and also can help carrying the heat away from the structure as it's being printed. The formulation can handle an arbitrary number of constraints, which you can impose in a subset of candidate materials or in subregions of the design domain, or in a combination of the 2. The only thing that you need to define the constraints are the set of material indices Mj associated for each constraint, and the set of element indices associated with each constraint. For example, if you have a constraint that imposes a maximum volume fraction for material 1 in all the design domain, you only need to select the material indices to be 1 for material 1, and the element indices will be all the elements in the finite element mesh. And to solve the thermomechanical problem, we solve a weakly coupled thermomechanical problem in which we first solve the steady state heat equation, given that we have some heat sources. And then we use the temperature distribution from the heat equation to solve the mechanical problem to find the displacement fields. Another important part of this formulation is the design variable update scheme that we adopt to solve this problem. So this design variable update scheme is based on a concept that we call sensitivity separation. And the concept of sensitivity separation is similar to OC, in which you have a linearly decreasing term as shown here, but we add another linearly increasing term, B transpose Z, which when we add these 2 terms together, we obtain a non-monotonous convex approximation of the objective function. Using this monotonous convex approximation of the objective function, we have to select the values of A and B in a way that we separate the sensitivity of the objective into a positive and a negative component, such that the convex approximation is well defined. So we have shown that this approach is very efficient. It's as efficient as OC and can help you solve problems that are non-self-adjoint. To summarize the framework that we implemented, we use the thermomechanical topology optimization statement that I showed 2 slides ago to design both the main composite structure as well as the support structure. And first, we have an initial design domain, and we have some given loads, which can be mechanical loads, thermal loads, or both. And then we use this optimization statement to find an optimized topology. Here we show a topology that is just a single material topology, but remember that the optimization statement works for multi-materials. So having this structure, we want to print this structure. In order to print this structure, we define a different problem now for the design of the support structures. To do so, we define a print orientation phi, and then we rotate this structure and project it onto a secondary mesh, which we call the AM mesh or additive manufacturing mesh. And we use this blue structure here as a passive region for this new problem. Then we impose a new thermomechanical boundary conditions, and we utilize the same optimization problem once more to obtain the red structures that are going to be our support structures. So to apply the thermomechanical boundary conditions for this new problem, we do so in an approximate way, such that we first conduct an overhang detection algorithm to find the regions of the structure that need support. So those regions are those whose overhang angle is greater than a threshold, than a critical overhang angle, which is defined by the printing process. So once we define the regions that need support, then we find the nodes and we tag them. And to all of those nodes, we impose mechanical loads T bar and a heat flux Q bar to represent both the weight of the structure that we want to print and the heat sources that come from the additive manufacturing process. In addition to adding these thermomechanical boundary conditions, we impose a length scale control to the optimal designs. And then we do so taking advantage of the generality of the volume constraint that we define. We can define regional volume constraints and apply a volume constraint to each one of these regions. And by imposing a local volume constraint to individual regions in the design space, we can indirectly control the maximum member size in your structure. And this can be seen more clearly in this slide, in which, for example, if we have 24 constraints, we get this kind of red structure, but as you increase the number of regional constraints, we get finer members, thinner members for the support structure. And this has benefits that are twofold. First, we obtain members that are thinner, so they are easier to remove. And second, we obtain a more even distribution of support structures, which comes in handy to support the structure when you print it. As a test case, I show a case study that is inspired by an antenna support bracket shown here. And we do a 2D model of this bracket in which the design domain is this one, subjected to a vertical load P and a bending moment M. And we discretize the design domain using 50,000 polygonal finite elements. And here's the distribution of elements in the mesh. For this problem, to design the main composite, we define 3 volume constraints, 1 per material. So constraint 1 controls material 1, so M1 is equal to 1, and controls the entire design space. Constraint 2, material 2, and constraint 3, material 3. When we use the topology optimization statement, we obtain this composite structure. That's the one that we are going to print. So now we use the topology optimization statement for the support structure, and we can define any AM design domain depending on the print direction that we want to choose. And if we use the topology optimization statement, we obtain these kind of structures. And as you can see, we get these branching like structures that is a direct outcome of the thermomechanical formulation, which is very nice if you want to remove the support structures afterwards. So if we use the length scale control here, then we can control the complexity of the final designs. So here, for a fixed volume fraction, we can decrease the maximum member size and we can obtain a nicer topology for our optimized support structures. To conclude this presentation, we present a multi-material formulation to solve thermomechanical topology optimization problems and use the concept of sensitivity separation to introduce a new design variable update scheme to solve the problems that are not self-adjoint. Then we can use a regional volume constraint to control the length scale, which allows to obtain better distribution of support material. And something that I did not discuss in this presentation for the sake of time is that we also use this method to construct the smooth Pareto fronts, and you can find the details in the CMAME paper. And with this, I would like to conclude, and thanks all for attending.
Thank you very much. Thank you. Are there any clarifying questions? So maybe you can comment on how realistic it is that you take a kind of static model for your thermal problem, because I assume that you're looking at powder bed processes, and so that means you have a layer by layer process. So how realistic is that to model that as a static thermal process?
You are correct in your comment. Actually, this formulation is a simplification of the actual process, and it is not accurate in the sense that we do not consider the layer by layer process. The way in which we impose the thermomechanical loads is an approximation. Here, for example, this T-bar approximates the weight of the structure that we want to print, and we impose Q-bar as a heat source, which is merely an approximation. But by imposing this kind of loads only in the regions that need supports, we simply want to encourage material to show up in those regions so that our print will be successful. But it is not an accurate approximation of the actual building process by any means.
No. Thank you very much. Any other clarifying questions? If not, thank you very much. Then we go to the discussion part of the event. Before we move into the discussions, I would like to thank all the speakers, particularly because maybe people sneak out. I also would like to thank very much Yunwoo for taking this very nice initiative. It was a great idea to set up such a webinar. The number of people who wanted to participate is overwhelming. And I would like to reiterate, if you have suggestions, please send them via email to us. We are very pleased to incorporate them in the next session. So having said that, who can I give the floor to open, to start a discussion? This is the same as happens during my online lectures. Nobody dares.
So I actually have a question for you, Oliver. So you're doing this update scheme, and I'm just curious, since I always just use MMA and honestly don't always think too much about it. Could you give a few comments on how much a speed up you get by this update scheme compared to MMA, for example?
Okay, so we use this update scheme, which is tailored to solve this kind of problems in which we have an objective function which can have positive or negative gradient, and we have linear volume constraints imposed in subregions. We obtain a significant speed up compared to MMA. I have the values in the paper. I can actually look at it right now, but we get a significant speed up using this new update scheme. And the reason for the speed up is that we can solve the problem, the sub-problems exactly as compared to MMA that you have to solve the sub-problems numerically. So if you give me 1 second, I will pull out the paper here to tell you the speed up obtained here. Can I share my screen again?
You should be able to do so.
Okay.
At least I don't think that you have been removed from the list. Yeah, that's fine.
So this is, for example, one of the figures that we obtain comparing our results with MMA. So in terms of defining element analysis, there is not much difference. But if you look at the green box, this is the update scheme. This is the computational time using our method, and this is the computational time that we obtain using MMA. Here is when we consider more regional constraints, and overall, we obtain an update scheme that is more efficient in this case than MMA, because the update scheme is basically tailored to solve the problem that we want to solve.
So does that mean in some sense that the MMA subproblem simply doesn't converge? So you're maxing out the inner iterations, or how should I understand this?
Not necessarily. In this way, we update the design variables in a way that is very similar to OC. So we can update all the design variables exactly and only find the Lagrange multiplier using some bisection method, for example. In MMA, you would have to use some quasi-Newton solvers to find the update of the design variables, and that's not the case here.
Great. Thank you very much.
Thanks, Niels. In the chat, I found that Wei Chen has a question. So, Wei Chen, please take the floor.
Yeah, so thank you. Every speaker filled the nice presentations. I have a question for Wenjing about using the machine learning-based approach for topology optimization. I think there's a growing interest in this area. On the other hand, I think there's certainly some situations that the traditional topology optimization approach will be more applicable. So I want to hear her insights in terms of what type of problems will truly benefit the data-driven methods or the machine learning-based approach. We cannot hear you, Wenjing. You muted yourself.
Well, first of all, I think it really depends on the application areas, application problems. So as I said, so this data-driven method, since it's data-driven, so it needs a lot of data, right? And to create this data also takes time. So if you only have a few, like single design problem, that's definitely not useful to use a data-driven. So I think in terms of the design of this heterogeneous material or functional gradient material, which you need a very large set of microstructures with different properties, data-driven could have some advantage. Second of all, I think those well, some areas require, like those layouts require certain shape constraint. And so those shape constraints, I think a data-driven method may have an advantage because you can very easily to implement some of the shape constraints. So these are the, since we're also doing this very recently, so we're still exploring, right? Figure out what type of problems will be truly benefit for this data-driven method. So these are the so far what we think about, can think about.
Yes,
Chen, you want to follow up? Okay. Any other questions for any of the speakers?
I could follow up on the last question, Wenjing. You showed an example with designing negative Poisson's ratio. So now, first question is, if I wanted to design now a positive Poisson's ratio, would I have to retrain the network? And two, did you compare the best value from the training set with the best value coming out of the network?
Yeah.
For your
Yes. The best value come out of the network. I think it's gonna be close. I didn't show it. There's another example we did, which is using minimal compliance design, right? In that case, we compare our design from network with the best one coming from FEM based simple method, and they are quite close. Okay, the difference is very small. Okay, that answers your second question. The first question is, if you want to design the Poisson ratio with Collet value, yeah, you need to redesign, retrain, but there's something you can do to reduce the number of training data. So the effort will not be too much.
But so it means every time you change either objective function or add new constraints, you would have to retrain.
For that neuron-based surrogate model, yes, that's true. So for example, in the design network, which you connect again with the conventional network, right? So that can be relatively more general in the sense of, because currently these two parts are separate trained, right? So the generator only generate the structures, while the CNN is to map the structure with its properties. So because there's a lot of work actually develop CNN for different type of problems, predict stress in fluid mechanics, stuff like that. So that part, you don't have to develop again. You can just using the the shared network, right? So that can save a lot of time. And for the generated part also, now if let's say in the ideal world, right? If everybody share the results, right? If we're all working towards the same goal, and we can build database, right? We can have a very powerful generator to create the different structures, or some small generator. Just you can build a library for different generated models, create different structures. These things, once you build, you don't have to rebuild again. You can save them as a library. So that can speed up a lot of time.
Thank you.
Thanks. Any other questions? Maybe for one of the other speakers?
Yeah, could I ask a question?
Please go ahead. Maybe you say your name and...
My name is Bing News from Dalian. I want to ask Pierre. Hi, Pierre. Can you hear?
Yes, we can hear you. Just go ahead.
Yeah, okay. Pierre, I want to ask you, so for very complicated optimized designs, you want to get the industrial design, so there are some transition. You have smoothing or maybe some other treatment. So I want to ask you, do you have any automatic tool to this transition, or you have some manual, how to say, treatment during this transition?
Right now, it's not automatic, fully automatic, but it's improving very fast. It's more people from the CAD design who are doing that kind of job. So we were lucky because there was a team of that kind in the consortium. But in the time we did the topology optimization, we were in front of what they could do. So we had to do the chain manually. But I have the great hope that very soon we will be able to chain all these digital tools to come to really smooth shape and so on. I think in 1 or 2 years, they made so much progress that we can hope that it will be available soon. But you're right, this is a very nice question. Yeah.
Yeah. Thank you.
Thank you. Any other questions for any of the speakers? If not, then I would like to thank once more all the speakers. Yeah, Niels.
Yes, I was just.
You're just in time. Just in time.
So, Julián, I have a question for you. So you are into the lattice structures. So, I, of course, aside from the problem of getting powder out of a plate structure, would there be any hindering in doing what you just showed us with plates instead of, or shells instead of the struts?
No. So if your question is, can you take this methodology and then just replace the bars with plates, then the answer is yes.
And then the follow-up question, and then introducing a hole so you can actually get out the powder. That would be the real trick.
Yeah.
Right?
So in our 2016 paper on plates, what we did was take the projected plates and actually multiply them times a kind of a freeform density field, so that it would actually make holes on the plates. But it wasn't nice because it almost becomes like a variable thickness sheet problem. And so the holes were not kind of sharp perpendicular cuts to the plates. They actually had like a variable thickness if you looked at the plate, right? We think that the clean way to do this is that you would have other geometric primitives that are like holes, and then essentially they cut into the plates. And so I think this can be done, but we haven't attempted that. But you're absolutely right. You should be able to get sort of these structures that are more like almost like honeycomb or foam structures, but with holes so that you can remove the material.
So I guess you need some funny constraint that can order the location of your holes.
So my personal sort of desire would be to not do that, but just have all the geometric primitives to represent holes, and then just let the optimizer do whatever it wants to do. So you then would have to impose some sort of, for example, permeability constraint. So you build it into the optimization. So that may be one way of doing it. Yep. But I would say, oftentimes having an open cell is not enough to easily remove material. It depends on the method of removal that you're using. If it's a polymeric material that is a sacrificial material, then I think it works very well, and I think that would work in this case. But if it's metal and then you're trying to remove powder, then just having an open cell is not enough, depending on the type of method that you're using for removing the powder, I guess.
Thank you. Any further questions? I try again.
Paulo? Yeah. So I had a question to Emílio. So Emílio, you presented a level set approach, but nevertheless you had like two SIMP powers, like 1.001 for the stiffness and 0.5 for the stress. So in my eyes, that sort of more points to a SIMP approach. So could you sort of elaborate on why do you call it a level set approach and not a SIMP approach when you have these parameters in there?
Okay, so in the case of the constitutive tensor, essentially that actually this exponent is not a kind of penalization, just an exponent that allows us to differentiate the constitutive tensor in relation to the level set function. So regarding this, the other function that we have, the psi function, that Q exponent is it's a kind of try to enhance the stress values of the sample, the stresses in the sample points that are cut by the boundary. So it's a kind of I would say way of doing some way of continuation in the function, a kind of penalization. So it's but it's a different idea than it's not like in the SIMP when you in the case of the constitutive tensor, it's not there for penalize, it's just there for so we can differentiate. And in the case of the psi function that is multiplying the stress constraint, then okay, there we are trying to do some kind of discrete, try to get some discrete behavior in that function. I don't know if I answer your question.
So it wouldn't work so well if you picked the wrong Q value. Is that what you were saying?
Yeah, you have to, as I said, if you use a small value of Q, then we get some high oscillations in the stress constraint. So we adopted Q equal to half. So I have to choose the appropriate value for the Q.
Thank you.
Wei, you have another question?
Yes, I have one for
Please go ahead.
After the projection-based method. It's very nice to see you give some very good example of results using like for multi-material design. I just wonder how computationally feasible the approach is if you want to design a very large, like aperiodic structure. I think your structure seems to be, the example you showed more at the, I call unit cell level. But if you want to do a big complex structure using the same approach, how computationally feasible it is?
I think if you, well, I guess there are several answers to that. One is that if we start considering the possibility of changing the design, let's say within the interior of a component, right? How valid is the homogenization sort of assumptions if you do something like that? So that would be one consideration. But if you're willing to live with the with sort of that assumption, then I don't think it's too computationally intensive. I think the real problem in terms of designing a component that has these lattices, it's really material failure constraints like stress and fatigue. This is to me the biggest challenge, because I think in terms of stiffness, we can do something that is fairly reasonable. But if now you start considering, stress or fatigue constraints, and particularly if you're starting to consider stress constraints between the lattice and, let's say, a coating, then I think that's pretty challenging, both from the point of view of the formulation, but also computationally. So if we're just talking about compliance, then I think it's fairly doable. And as a matter of fact, we're currently working on a method along the lines, for example, of some of the work that Jerome Groen and Ole Sigmund have done of designing these coatings with lattice infills. We're doing something similar where we have a coating, but we have one of these truss lattices. And so it can be done, and it can be done in a reasonable amount of time for compliance. But I think if we start thinking about sort of more realistic failure criteria, then I think it becomes a much more challenging problem.
Thank you very much.
Thank you.
Any other questions? If not, then I would like to make one more advertisement, and that's of course for June 25, when the Danish colleagues Ole Sigmund and Niels Auge are going to organize a similar session, but then early in the morning in Europe. So then hopefully also people from Australia and the Far East can easily join. And with that, I would like to thank all the speakers and all the participants. We apologize that quite a number of people have been locked out because the Zoom account was too small. For those in Asia, I would say sleep well. For those in America, have a nice day. And for Europe, have a nice evening. See you all on the 25th. Bye-bye.
Bye-bye.